Alright guys, this is the study session over momentum number 1. Number 1 says two trains are moving towards each other at the same speed on the same track. Upon colliding, the trains lock together. If one train has twice the mass of the other, what will the ratio of the speed of the trains after the collision to their speed before the collision be? Now, it needs to be noted here initially that there are no numbers given. So we're going to attempt to do this whole problem without any numbers. First of all, we know that one train has a mass m, train 2 has a mass 2m, and then in the end, they're together, so they have a mass of 1m and 2m, which adds together to be 3m. Alright, they're going to have some final velocity, and we don't know what that is yet. So we're going to know that the velocity of this guy is v this way, and we know that the velocity of this guy is v that way. Alright, now we're going to plug this in. Momentum initial equals momentum final, and to find the momentum initial we have to add up our two momentums here and here. So momentum 1 is mass times velocity plus 2m times negative velocity. Why do we make it negative? Because it's going the other direction. That's equal to the the momentum on the other side, which will be equal to 3m times vf. Now the reason these v's are the same is because it says they were going the same speed. So if you'll refer back to your problem, it says they were going the same speed but in opposite directions. Okay? And so what we do now is we're going to try to solve for vf in terms of v. Now, the first thing we're going to do is go mv minus 2mv equals 3mvf. Now you should notice that these are like terms, so we can add them, just like we could add xy plus 3xy. We could add that up and get 4xy. That's what we're doing here. We're going to add these two together, and we'll get negative mv equals 3mvf. Now, we're going to divide through by 3m to get vf by itself, and that gives us negative 1/3 v equals vf. So that means the ratio of our final velocity to our initial velocity is 1/3. And this negative sign can make a difference, or it can't. It just doesn't really affect anything too terribly much. It just depends on which direction you made this train go. All right. If you'd made it go the other way, it wouldn't have come out positive. So it doesn't really have an effect on this problem. The important part is the 1/3 that we got there. That is the ratio of the initial velocity to the final velocity. Alright, let's see if we can get number 2 in this first little video as well. A braking force is applied to a 300 kilogram motorcycle to reduce its speed from 20 meters per second to 16 meters per second in 10 seconds. A, find the change that has taken place in momentum of the motorcycle, and then B, find the braking force. Alright, so for A, we need to find the change in momentum. And the way you find the change in momentum is you do the mass times the final velocity minus the mass times the initial velocity, or we can factor the mass out of it and just get change in momentum equals mvf minus vi. So we would get, in this case, change in momentum equals 300 times 16 minus 20. And we would get change in momentum equals negative 1,200 kilograms times meter per second, or 1,200 Newton seconds. Okay? For part 2, it says, what was the braking force? Well, you'll have to remember that the braking force is going to be applied via an impulse. An impulse is equal to force times time, and that's equal to the change in momentum. Well, conveniently, we know the change in momentum is equal to negative 1,200 Newton seconds. Now, the reason I'm going to use Newton seconds is because it's force times time over here, and if I divide by a second, like the 10 seconds that it gave us, we end up with a Newton, which is the correct unit for force. So the force should be equal to negative 120 newtons. Okay? So that is question 1 and 2 from the review.